All right, everybody. Your laptop shut and all that other good stuff. I hope you had a good break. Good to see you back, see all of your kids back. Fall is here. Okay. When's Halloween? Tuesday? Tuesday, right? So we get to choose either on Monday or on Wednesday, maybe Wednesday. You have to come in costume. Right. This is tradition every fall. On the day, either on Halloween or the day after Halloween, you're going to come in costume. Give me just a mask, anything, but have some fun. And I'll wear something too, and yeah. We'll record this and post it on YouTube for posterity. Oh no. What happened? Okay, let's begin. Welcome back after the break, and thanks for making it in on a cold fall morning. We're going to continue our series of lectures on recurrent neural networks because we know it's the most exciting topic in the world, and that's exactly what you want to be doing at 8 a.m. on a fall morning. Please shut your laptops, guys. And let's start. How many of you want to be here? How many of you think this is really exciting? At 8 a.m. class, it's cold outside. Yeah. And there's nothing you'd rather be doing than in class listening to a lecture on deep neural networks. So. Thank you. Can you shut your laptop? Unless you've got. Thanks. All right. I don't know about you, but this is not where I want to be just now. But anyways, here we are. So here's the story so far to pick up exactly where we left off. We were speaking of recurrent neural networks, and we said that recurrent neural networks can be trained by minimizing the divergence between the sequence of outputs and the sequence of desired outputs. And the fact that you're always dealing with sequences potentially cause problems, because how do you compare sequences? Unless you have a one-to-one correspondence between what goes in and what comes out. And very often, if you're doing something like recognizing speech, translating language, you're not going to have this kind of correspondence. So today we're going to be looking at one such problem where you don't have a clear one-to-one correspondence between the input and output, but you have something called order correspondence. So here are variants of recurrent neural networks. The one to the left is just a conventional MLP. There's nothing recurrent about it. Each input is processed independently. The one to the right is a synchronous recurrent neural network, where corresponding to every input, you have an output. For example, if you were predicting the stock market on a daily basis, or if you were looking at a sentence and you are trying to assign a part of speech tag to every word in the sentence. Now, the one to the left on this slide is the kind of network you would use if you had to analyze an entire sequence of inputs and then make a prediction at the end of it. For example, if you're doing sentiment analysis, you'd have to look at the entire sentence all the way from the beginning to the end to make sense of whether it was saying something happy or something sad. And the one to the right is the one that's particularly relevant to our lecture this week and also to your homework 3. And here you have something interesting. The input and output are not one-to-one, but they have order correspondence. So what I mean by this is that the first portion of the input over here, the first two vectors in the input correspond to the first output. The next two vectors correspond to the second output. the next 3 vectors correspond to the third output. So if you reordered the input, the outputs would change. They're sort of coupled to the input. In terms of arrangement, there's a strict order correspondence, but there is no time correspondence. It's not one-to-one. And that causes problems. So, and then you can have others. The one to the left, of course, the famous machine translation problem we spoke of. You have to look at the entire input before you generate your output. Or if you are captioning images, you just take a one-shot look at whatever it is you're generating data for, and then proceed to generate data from there on, right? So let's consider this first one. This is an MLP, right? How many of you think we can use an MLP to analyze a time series? How would we do it?
You would shift it, like we would do the CNN image, you could shift it over time.
Perfect. So all we'd have to do is to just analyze every single input independently, right? But then how do you make this sort of account for the fact that this is a time series you're analyzing? Any guesses? Yeah.
Maybe just like put it in the final sequence and compare this sequence.
Beautiful, right? You just look at it. The fact that you're analyzing a time series is sort of baked into the loss. You're comparing sequences to sequences. And hopefully, the loss sort of guides the rest of the network below. So if you go back to several lectures ago, 2 lectures ago, we were speaking of partially recurrent networks. In partially recurrent networks, there was no real back propagation through time. Nonetheless, if you compared sequences to sequences, you would sort of expect that it learns something about the sequence structure of the data. And then, so here's what you would do, right? At each time, you would have a divergence. And the divergence is going to be, so the divergence between sequences, this is a situation where you have a strict one-to-one correspondence between inputs and outputs, right? So the divergence between sequences can technically be decomposed as the sum of the divergences at individual times if you have correspondence. And so the special case would be this one here, where the actual divergence between the target sequence and the output sequence is the sum over time of the divergences at individual times. And correspondingly, if you computed the derivative of this divergence, which is the divergence between 2 sequences, with respect to any specific output, simply because these other divergences, what happened, do not, oh, come on. Simply because these other divergences do not influence this local divergence. So the derivative of the accumulated divergence with respect to any given input, any given output, is simply going to be the derivative of the local divergence itself, right? So easy enough. Why is my thing flying? I'm sorry. Pardon me. I need a different clicker, right? So here's a point. Okay, time's up. Katrina, what's the answer to the first one? And Quentin, second one. Also true, right? So Pokemons, there aren't many of you in class today. Today we will actually post class attendance. This is the second half of the semester. I usually kind of take it easy in the first half of the semester because people do pay attention. But this is when it gets cold. This is when it gets uncomfortable. And this is when you're supposed to be in class. So your attendance from today on counts. And because I'm going to largely discard everything we did before the break, it counts twice. Just to let you know, right? Anyways, both statements were true, right? So now let's go and look at your regular MLP of this kind. This one is where the network produces one output for each input with one-to-one correspondence. For example, if you are assigning part of speech tags to words. And so, of course, in order to decide if the word yellow was, a name or an adjective or a verb, you'd have to look at everything that happened before and after, right? So you need recurrence. But then every single word in the input needs its corresponding tag. And so you could do this either one-sided, where you analyze the input from left to right and then assign tags. This would be a causal process in that as soon as you saw each input, you would assign the tag and then move on. Or you could be looking at it bidirectionally, which would make more sense if you were actually looking at the part of speech tagging problem, because information about what part of speech any given word is also encoded in the words that follow it. And so here you could have a bidirectional recurrent network. Nonetheless, the actual tagging is for tags that are assigned to every word. So even though the network is bidirectional, you have a strict one-to-one correspondence between the input and output. And so, of course, I'm going to continue assuming that we have one-sided networks, but there's nothing special. You could be thinking of bidirectional networks here as well. And so here we know exactly how to compute derivative divergences and back propagate them. You would be computing the divergence between the output and target sequences. And the assumption here is that this divergence, whatever it may be, can be differentiated with respect to every one of the outputs. If you couldn't compute that derivative, there's no derivative to propagate backwards. And then once you do that, you can just go ahead and use BPTT, back propagation through time, to train the model. Now, so here, of course, for back propagation through time, starting from the final time instant, going back, you would need the derivative of the divergence with respect to every single, the output of the network at every single time. So the assumption is that you are able to compute this derivative. Now, again, because you have one-to-one synchrony, it is convenient if your divergence is so defined that it's merely the sum of the divergences at individual instants. If you could define your divergence in this manner, then the derivative of the sequence level divergence with respect to any given output is simply the derivative of the local divergence at that time with respect to the corresponding output. So if you could assume that the divergence between these two sequences is simply the sum of the divergence at individual instants, then the derivative of the global divergence with respect to any given output is simply going to be the derivative of the local divergence with respect to that output. It makes things very convenient. It's because things are easy to compute. So much of what we will do when we are faced with problems like these, where there is no strict correspondence between, or there may be no strict correspondence between the output and the input, is to try to convert the problem to this format where you can think of divergences in terms of local divergences. Because once you do that, then the problem becomes much simplified. And so here's your second problem. Okay, guys, time's up. So Pokemon Miltank, what's the answer?
First one is true.
First one is true. So there's only one corresponding output corresponding to every input. And the divergence can always be thought of in terms of conditional inputs. Well, the divergence between the true and desired outputs can have an additive contribution from the output at each time, right? The key word is can. We're not saying that it will always have it, but we're going to try to convert everything to that format so that we can perform back propagation conveniently. So, but first, let's begin by looking at this problem, right? Where you have an entire sequence of inputs and then you make a classification. For example, sentiment classification for a sentence, right? Or better still, a nicer example for me is when you're performing speech recognition. So if I give you a segment and I ask you, does this segment represent the phoneme R? You just want to look through the whole thing. And then at the end of it, you make a decision, right? As you go through the little snippet of recording, you sort of accumulate evidence. And then when you come to the end of it, you decide. Now here, so problems like question answering. What is the color of the sky? You have to get to the last word before you reply. You can't reply at any other time. Or, phoneme recognition. You have to see the entire sequence and you sort of accumulate your evidence just to be sure, and then you call out the answer. So here, the thing is that the exact input sequence is provided and the output is generated when the last vector is processed. Now, the output is not, as always, the output is not just a definitive answer. This is X. The output is going to be a probability distribution over the possibilities. This is always the case, right? But then, what is the actual computation that happens over here? When I have a classification of this kind, right? Remember what was unique about recurrent neural networks. Every column was identical, right? We were basically using the same network at each time and just pulling in information from the past to make a decision. So what does that tell us about the outputs at other times? Here the final output is being computed at time 2, but what about at time 0 and time 1? Are we computing outputs? Mm-hmm. So the fact is that the network actually does compute these outputs, you just ignore them. And you call out the output that you do see when the final vector has been processed. And that's simply because the network is very symmetric, right? Every column is identical to every other column. And this is what we're going to try to exploit. So when I'm training the model, here's what I would do. The classification is, I have, for example, a little snippet of a recording, and I'm informed that this is the phoneme R. Then I would perform my training as we would normally. You perform your inference, and then you look at the output you get once inference has been completed, and compute your loss. So the inference would be performed at the last frame, at the last input, at which point you're going to compare the output to the target output, and you compute your loss. And that loss, the derivatives of those loss are going to be propagated not just vertically down, but propagated backwards through time, all the way through to the very first input. And you'd accumulate derivatives. But then this is sort of losing some key information. And what is that? It has to do with the fact that you're only computing the loss at the very last instant, because that's how we've set the problem up. We're pretending that there's no useful information coming out of these intermediate outputs. But then consider phoneme classification. I'm just going, does it make sense for me to only wait till the last frame before I take my decision? What about the intermediate frames? What are those intermediate frames supposed to be? Is there no evidence at all about the final outcome? What would you say? So let's say I have 5 frames of the phoneme R. Is it only R at the 5th frame, or is it R elsewhere too?
There may be silence at the end.
So the thing is, there's R elsewhere too, right? So it would sort of make sense for me to say that I can smear that label over time and use the same label at each time, right? Because although I'm taking my decision at the final input, whatever classification I've performed probably holds true through the rest of time, right? And so once I do this, then I have this very simple, familiar setup again. Now I have a one-to-one correspondence. And then I can compute the divergence at each time. And then I can just say my total divergence is the accumulated divergence over all time. And just to make things generic, instead of saying that it's simply the sum of the divergences at each time, I'm going to call it the weighted sum of the divergences at each time. And you can choose your weights. So for example, if you were performing speech recognition and you were trying to perform the classification of the phoneme R, then at every single time, the phoneme R is still the phoneme R. So all the weights are going to be 1, or at least they're going to be equal, right? Whereas if you're performing question answering, then it doesn't make sense for me to be expecting that the correct answer is the word sky, the word blue, before I know what it is I'm asking the color of, right? I could have been saying color of rose, and blue would be completely wrong. So in that case, the weight is going to be 1 at the final time and 0 at other places, or some other reasonable choice, right? Nonetheless, the key point is that it makes sense for us to simply repeat the target value over time, compute divergences at each time, and then take an accumulated divergence over time. So you've taken a problem where the label only arrives at the final instant, and you've converted it to a time synchronous problem. Yes, Jacob?
In the speech recognition task, are we assuming that in this example, all 3 of them have like this sound R, or if it's just the one in the center?
No, all of them. You're just assigning the same label to all of them. You're just claiming that you can smear the label over the entire thing because they're all the same thing, right? So that makes sense to you guys? Questions? Because we're going to build off this. Right. So this is what we will do, okay? Now, so we're done with this problem where we've analyzed an entire input and then produced an output. And it's very easy for us to see how inference is done. You just analyze the entire input, produce an output at the end of it. It's very easy for us to also see how training is performed. You analyze the entire input. You produce outputs at each time. You can just grab the label at the final time, drag it over the entire sequence, and then you're going to get divergences at each time that you can sum up, right? And that can be used for backpropagation through time. No big deal. Now things get interesting here when I get to the problem of time synchronous but order asynchronous classification. So here, the input comes in, it's sequential as before, and the output is order aligned with the input, but the problem is you don't know where in time the output symbols must occur. So here's the situation. For inference, you're given this problem. You're given a sequence of inputs, and you have to asynchronously output a sequence of symbols. Once again, think of the problem of speech. I give you the word hello, and you have to output her, la, and o, right? You know that this, at least in principle, you could know that the sounds are these 4, h, and her, la, and o, but where exactly do you output them? For this, you would need to know where the her ended. You would need to know where the a ended, where the la ended, where the o ended, and nobody's marking these things for you, right? You just got the entire recording, and they're going to get 4 outputs, and you don't know where they are. And in fact, more generally, if you're just looking at recognizing speech, you wouldn't even know how many outputs to produce, let alone knowing where they must be produced. So the output is order synchronous with the input, but the challenge is that there is no idea of where the output must be generated. Now, the point really is that what you're really doing is computing outputs at each time. As we said before, every column is identical to every other column. So you're always computing outputs. The real problem is not of generating outputs. The problem is that of knowing where to read the outputs. You're getting some outputs at every time, and you're supposed to read just some of them, but you don't know which ones to read, right? And that makes things difficult. That make sense? Right. So, well, if this is the case, how do I determine where to read the output? Does anybody have any suggestions? Yeah.
Like, just as you can have a probability distribution at the end, read the output one first, like we'll change to the next one.
That's actually a pretty good idea. And we do something very similar, right? So here's what we would do. At each time, the network isn't just outputting a single label, right? It's actually computing a probability distribution over all of the labels. And so if those 7 labels were the ones that you were interested in your vocabulary, in your set of categories, then at each time, it's going to compute a probability for every one of those 7 guys. And so over time, the network is actually computing an entire table of probabilities. The probabilities for all the labels at each time. So every column in the output is going to sum to 1, right? And so what you could do is simply pick the most likely one at each time. Now again, so the thing to remember that a neural network with a softmax or logistic output is actually computing an estimate of the a posteriori probabilities of the classes given the input. And if you have a left to right neural network, it's actually computing the a posteriori probability of all the classes given all the inputs until that time, right? And your general approach of selecting the class with the highest probability is simply performing maximum a posteriori probability estimate classification, right? So it's a map estimate. We're going to use the same principle here. Now, remember, the problem that we are actually trying to solve is a little complicated. And what is that? I'm given a sequence of inputs, which could be, say, x1 through, say, x100, right? Or x0 through x100, depending on how you index it. Now, let's say my phoneme sequences, my set of labels are, let me call this L1, L2, and L3. So these might be 3 phonemes, right? What are all the possible outputs in this case? What are all the possible outputs? The output could just be a single L1, right? It could just be L2. It could just be L3. So what this means is that I could be just producing an L1 out here, or an L2 out here, and an L3 out here with nothing else. So the final output is out here, right? Or it could be L1, L1. It could be L1, L2, and so on. L3, L3. All of these combinations are possible. But once I get to just combinations of pairs of symbols, what is the problem here? Anybody? What would the problem be? Just looking at that, you know that you have to output consider this guy, right? You know that you have to output an L1 over here. You have no idea where the other L1 happens, right? Or if I were outputting this one, L1, L2, you know that this last one is an L2, but where's the L1 happening? No idea, right? And then you also have L1, 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 all the way through L3, L3, L3. So these are all the possibilities, right? And so you can have sequences, the output, you do not know how many symbols there are in the output. It could be 1, it could be 2, it could be 3, it could be all the way to 100, right? And so the number of possible outputs is extraordinarily large. And what you're really trying to do is to pick the one sequence, something out here, which has the highest probability given the input. Does that make sense? Again, we are performing maximum a posteriori estimation. Anytime you perform classification, again, I remind you, what we are really doing is picking the class with the highest probability, right? In our case, a class is a sequence of symbols, except we do not know how long the sequence is. All we know is that the sequence can be anything, have a length of anything between 1 and the actual number of inputs. Make sense? Right. And so we are trying to pick the sequence. So you will note that I have x0 through xn minus 1 over here, indicating that the input is n long, and s0 through sk minus 1, indicating that the output is k long, where we do not even know what k is. All we know is that k is no greater than n, right? It's anything between 1 and n. Okay? So this is what we'd like to do. Now, how can we do this? Here's a very simple approach. I can just pick the most likely symbol at each time. And so if I pick the most likely symbol at each time, now here's the thing. If I pick the most likely symbol at each time, this naturally is going to give me sequences which are as long as the input itself. But that's not what we want, right? We want to have the compressed sequence. So given this, let's say I just picked all of these guys. We know that we want an output sequence that is up to the same length as the input, right? So what could we do? How would we derive that?
You skip repetition.
I can skip repetitions. I can merge things, right? And so this is going to give you something of this kind. What would the problem with this be? Anyone? What?
I don't know whether the first instance is to be skipped or the latter one.
You cannot distinguish between repetitions, genuine repetitions, and repetitions due to extension, right? You can't really make out the distinction between these two. So we have this problem. Nonetheless, and also the resulting sequence may be meaningless. So, you're imposing no structural constraints. Nonetheless, let's assume for now that there are other ways of you can be smarter. You can impose external constraints saying that whatever sequence you pull up must match, the words in a dictionary or something of that kind. But in any case, for now, let's just assume that we have some idea of how to perform inference. We're going to return to the problem of inference, but for now, we'll assume that we know how to perform inference, okay? And so our approach for inference is that you just pick up the most likely symbol at each time and then just merge repetitions, and you're going to output something only at the final time in a sequence of repetitions, okay? So problem solved, right? But here's the thing is, here's the thing. When I'm picking, what I really want to do is to pick the most likely sequence, right? Which could be as long, whose length is unknown. And what I am doing instead is picking the most likely symbol at each time and then compressing those. So will picking the most likely symbol at each time and then eliminating repetitions necessarily give me the most likely short sequence? Anyone?
No.
No. Okay, why not? We'll get to that later, okay? The answer is indeed no. But, so here are the two questions, right? The first one is, how do we know when to read the outputs? We don't really, but we saw some sort of a half-assed answer. So let's assume that we have an answer for now. The second problem that is more important is how do we train these models, right? And so, oh, come on. So how do we train these models? This is the more challenging problem for the rest of today's class. Now, when you're given training data, you're going to be given the sequence of inputs and the sequence of outputs. For example, you might be given the recording for the word hello, and you're informed that this is the word hello. So you know that there are 4 outputs. There's a phoneme H, there's a phoneme A, there's a phoneme L, and the phoneme O, right? So you'll be given both of these. Or in my example, you have the word but, right? Same thing. And now just suppose that somebody told you exactly where each word phoneme ended. In other words, someone told you how to align your output to the input. And so for this, we're introducing the notion of alignment, right? You're informed exactly at which time each of these symbols occurred. Now, if I tell you that here's a recording, this represents the word but, then the symbols that can be output are the word symbols b and t. But they could occur at any time. And so there are many different ways of aligning but to this input. Here my input is 9 symbols long, right? 9 inputs long. My output has only 3 symbols. So the only thing you know is that t must occur at the final time, right? So how many different ways do we have of aligning but to this input? Anyone? How many different ways would we have? That's a lot, right? That's because we know the T must occur at the end. And so there are 8, in this case, we have 9 positions for A and up to 8 positions for B, correct? And so about 72. It's smaller than 72, but yes, it's still a large number, right? And you can imagine that as you increase the length of the input and number of symbols, this is going to go up pretty quickly. Now, just assume that some good soul came and told you in your training data exactly where each phoneme ended. So they told you this is the word but, and they told you that the sound b ends at time 2, ends at time 6, and t ends at time 9. Now you know where the outputs must be read off. And so then it's easy enough for you to compute the divergence at these three instances. And so the sequence to sequence divergence is going to be the sum of the divergences at these 3 times. And that divergence, the derivatives of those divergences, can be propagated backwards. But then when we do this, we are losing some essential information. What is that? We're ignoring something. We are sort of assuming that we're ignoring the information in the intermediate outputs, correct? And you really don't want to be doing that. And so you can just say that the symbol over each segment, the symbol is the corresponding symbol is smeared. And so you would say that B occurs for 3 instances, occurs for whatever 3 instances over here, and T occurs for 4. And this is how you'd compute your divergence. And so now the overall divergence is going to be the sum of these 10 divergences. The derivative of that overall divergence is what you're going to be propagating backwards, right? So far so good. But now here's the other problem. So if this oracle came by and actually gave you the times at which each of the symbols occurred, we know how to deal with it. What would we do if that information was not provided? So if you were not told exactly where the symbols happen. You're just given the recording, you're told that this is the recording for the word but. Compute the divergence. So what would you do? Or train the model. What would you do? Anyone?
Try everything that's like factorial.
Try everything. That's actually a very good answer. But if you're trying to be, an engineer, you probably guess the alignment, right? So we know how to train if the alignment is provided, but the problem is not that the alignment is not provided. So there are 2 possibilities. The first is you try to guess the alignment. And the second is to what Lawrence mentioned, consider every possible alignment, right? So guessing the alignment is something like so. You would sort of assume initially that here's where I think B ended, here's where I think E ended, here's where I think T ended, right? And then based on this, you could train your model. But then once you train your model, you can sort of use that model to go back and update your guess for the alignment, refine it, and then repeat the process, re-estimate, go back and retrain your model, use your retrain model, and go back and use it again to guess the alignment all over again. Now, so the key component over here is this one. You're given the model, you're given the input, you're given the output sequence. So here, for example, you're given, this is an iterative training process. You're given at any step in the training, you're given the current estimate for your model. You have the input, and you're told that this input corresponds to the word but. How do you use the model and the input and the knowledge that this is the word but to find out exactly where each of these 3 symbols must be output? So to go back, let's go back and look at this notion of an alignment. The alignment tells us which portion of the input aligns to what output in the output symbol in the sequence. So here are different alignments for but. And as we saw, you could have up to 72 different alignments in this particular example, right? And so when you're guessing, you're trying to pick the one of these, right? Just one of these alignments. And which one would you pick? If you're given a current model. The most probable one, right? You want to pick the most probable alignment given the current model. And so there's a reason for doing that. When we train our model, what are we doing? We are sort of training the model to maximize the probability of our data, right? The training data. And so if I give you an alignment, then if I train the model, you have two things. You have an alignment, and then you have the model parameters theta. This is unknown, and so is this, right? So what we can do is to say I'm going to fix my model parameters theta, and your likelihood, your loss is going to be a function of both the alignment and the model parameters, not just one of them, because the alignment is unknown. And so anytime you have a problem where you're trying to optimize with respect to two variables, here's a very simple solution. Fix one, optimize it with respect to the second one, right? Then fix this, optimize it with respect to the first. Then fix this, optimize it with respect to the second. And at each time, you're decreasing the loss. And so you're guaranteed that at each step, the loss is going to keep going down, and eventually you're going to arrive at a local minimum, right? So that's basically what you do over here. You're going to sort of guess an alignment, one of these. We're going to, and the specific one is you're going to pick the alignment which minimizes the loss, but the loss, as we know, is the negative log probability. So alternately stated, you're going to pick the alignment which is most probable, given the input and the current set of parameters. Make sense to everybody? Right. And so now the alignment tells us which portion of the input aligns to what portion of the sequence, and I can represent an alignment as repetitions, as we saw this, right? If I say that the phoneme, if you consider that first alignment, then if I say that the phoneme b occurs until time 3, that occurs from there until time 7, and then t occurs from there until time 9, it's the same as saying b stretches through till time 3, stretches through from 4 to 7, and t stretches through from 8 to 9, right? So an alignment can be thought of as representing the repetitions of symbols till they terminate. And now, when I'm trying to pick the most likely alignment, I'm basically going to be, one of the nice things about representing alignments in terms of repetitions of symbols is that now in the restated alignment, where I repeat the symbol at each time over the segment that it represents, the new representation is time synchronous with the input. So if I want to represent this alignment here, and this, if I want to represent, say, this alignment here, just like so, this has only 3 symbols, right? Whereas the input has 10 symbols. Whereas if I stretch this guy out and repeat it, and do those for each of these symbols, then the sequence in green has as many values as the number of inputs itself. And so in this modified representation, where I've just smeared the symbol out, the label sequence is as long as the input itself. And that brings us into familiar territory. So you have this notion, which is to say that if I've got a phoneme sequence b, now again, there's a notion of finding the most likely alignment, right? And what do we mean by finding the most likely alignment? If I've got this phoneme sequence but, b, and t, there are many different ways of aligning that sequence to the input, and which is the same as saying there are many different ways of stretching each of the 3 symbols so that together these stretch symbols consume the entire input. And so this is what I will call an expansion, right? I have this asynchronous symbol sequence but, and when I begin repeating the symbols, eventually I end up with a time synchronous symbol sequence. So this is what I will call an expansion. This compressed sequence, but over here, can be expanded in many different ways to align to the output. And conversely, I can have many different alignments which all compress the same reduced sequence. So the notion of an expansion and compression makes sense to you guys? Right. So many different alignments for an input can compress to the same unaligned compressed sequence. And so the problem of finding the alignment is simply finding the best expansion of a compressed sequence for a given input, given a model. So you're given the current model theta, and finding the best alignment is like saying, I'm going to find out which of these expansions is most likely. That make sense? Okay. So here's the alignment problem. You're given an unaligned k-length compressed symbol sequence S0 through Sk minus 1. And for example, I keep changing my examples, is the word beefy. And then you're given an input n of length n, where n has to be at least as long as the number of symbols in your output, right? So again, this is for training data. For training data, you know how many symbols there are. I've given you the input, which is a sequence of vectors, and I've told you that this is the word but. So you know that there are 3 symbols in the output, right? So you know k, you know n, and the constraint is that n must be at least as long as k, because again, you have order correspondence between the input and the output. And so our problem of finding the alignment can be stated in this manner. I want to find the expanded sequence, where the expansion is basically obtained by repeating things, right? So I want to find the expanded sequence that's most likely given my input and given the shorter sequence, the asynchronous sequence. I'm given the input sequence of input vectors. I'm informed that this is the word but. Find me the alignment. So again, find me the expanded sequence S0 through S minus 1 that is most likely given the symbol sequence and the input. Or alternately stated, find me the most likely symbol sequence, the time synchronous sequence that when compressed becomes my given symbol sequence, right? So search through all of the symbol sequences, find me the ones that when compressed will give me but, and then of those pick the one that's most likely, okay? So here's a point. Okay, guys, time's up. Pokemon matchup. That's Umuhoza Alice. What's the answer for? Is the first statement true?
Is true.
Okay. And Pokemon Steelix. What about the second statement? Steelix?
It's true.
True. Okay. And Pokemon Jolteon. Richard, what about the third statement?
True.
True. Okay. And Pokemon Crobat. What about the fourth statement? Dio? Pokemon Crobat, you there? Oh, okay, next one. Pokemon Gloom.
True.
Nice. That's Dio. He just came in. He was asserting that it's definitely true, right? So Pokemon Gloom, what about the fifth one?
False.
False. Thank you very much, right? So do all of you agree with those answers? Yes. Only the fifth one is false, right? An order aligned symbol sequence that's shorter than the input can be aligned to the input by repeating symbols until the expanded sequence is exactly as long as the input. And the alignment of an order synchronous symbol sequence to an input is a time synchronous symbol sequence, because now I'm going to have one symbol per every input vector, right? A symbol sequence that's time synchronous with an input can be compressed to an order synchronous sequence by simply removing repetitions, although this is not unique. And order synchronous symbol sequences that are shorter than the input are compressed sequences. If they are the same length as the input, they are time aligned, they are not compressed. But if they're shorter, then definitely there's been some repetition that has been removed, right? So here's the problem. Now, going back to our problem, I'm given this sequence of inputs, which is 9 vectors long in my example. And here, since I like to keep changing examples every slide, the example is the word, beefy, I believe, right? And so we have to find out how the word beefy aligns to this input. Now, you have a current model. The current model would have computed a vector of probabilities at each time. So if you pass the data through the network, you're going to get this table of probabilities, which is basically a sequence of probability vectors, right? So let's say the actual word sequence I have is the word beefy, right? Now, one simple thing I could do is to just say I'm going to pick the most likely symbol at each time. Will this necessarily give me an alignment of the word sequence I'm looking for, of the symbol sequence I'm looking for? No, why not?
May generate or like predict things that are not part.
So it's going to, you want an expansion of beefy, and this thing is going to be something completely unrelated, right? If you just, especially when you're training the model early in your training, the model is going to be garbage. It's going to give you all kinds of random symbols at each time. You can't just go ahead and pick the most likely symbol at each time. It will not work. So here's what else I can do. I don't want it to pick symbols that are not in my output sequence, right? So I know that my output sequence is the word beefy, which means there are only 3 phonemes, b, e, and f. So why don't I mask out all the guys that are not these 3 phonemes, right? So that means I'm going to be masking out these rows. And now focus just on the remaining rows. And now if I just choose amongst the symbols that are actually present in my output sequence and pick the most likely symbol at each time, will I get an alignment of beefy? Why not?
You may end up getting a repetition with something sandwich.
So you might end up with, okay. Basically what you're doing over here, when you're masking the rest of them out, here's a different way to think about it, is you're pulling out those 3 rows, creating a separate table which only has those 3 symbols, right? And then you're using those to decide how to align. And if I just pick the most likely at each time, although you're guaranteed that the symbols you get will be in your symbol sequence, there's no alignment, there's no guarantee that it's actually going to align to your symbol sequence. So here, for example, I've just picked up the most likely, and this has become the beefy, right? Which is not an alignment of beefy at all, right? So it's sort of, things are improving. Now we're not getting garbage symbols, but we're getting garbage sequences, alignments. So how could you improve on this? I want to make sure that whatever sequence I get is definitely the word aligns to the word. I mean, whatever I pick as the most likely definitely represents an expansion of beefy, right? So what can you suggest how I can take it one step forward from here? Anyone?
Mask the fee and at the first and not mask mask as a last.
Yeah, but still, is that going to be enough? That's a good step. Is that going to be enough? What can we do?
We somehow like track what we've predicted so far so that.
Again, it's, you're looking at the most likely overall sequence, right? So what could we do? So here's what I will do, right? I'm going to pull out all the symbols from the table in the same order in which they occur in my sequence. So if my symbol sequence is beefy, then I'm going to pull out the burr row and place it as the first entry on my table, my updated table. Then I'm going to pull out the E and make it the second entry in my updated table. I'm going to pull out fur, make it the third entry, the third row of my updated table, and then E again as the fourth row of my updated table. Observe that because here beefy occurs, E occurs twice, in the modified table, I actually have two identical rows, one in the second position and one in the fourth position, right? So subsequently, I'm going to just note that any alignment, once I arrange my probabilities in this manner, right? I construct this updated table. Then any alignment of the word beefy to my input is going to be a path through this table, a monotonic path through this table from the top left corner to the bottom right corner. Why? Because if it's monotonic, then you're always moving downwards and you're always moving forward, right? So which means that you're going to get a sequence of burrs and then you're going to move into E. You're going to get a sequence of E's, then you're going to move into fur. You're going to get a sequence of furs and then you're going to move into E again. So any path from monotonic path from the top right, top left to the bottom right will represent a valid alignment of the word of my symbol sequence beefy here, right? And so what are all the monotonic paths? To represent all monotonic paths, I can just construct this graph. From every box in my table, I can have an arrow going sideways and then one arrow going just immediately down. So if I do this, if I just follow any sequence of arrows from the top left corner to the bottom right corner, right? I'm guaranteed that it's going to be a monotonic path from the top left to the bottom right, and I'm guaranteed that it's a valid alignment of the word beefy to the input, right? And now these are all probabilities, right? I can think of the whole thing as a graph. And so, and I can think of each of the cells in the table as a node in my graph. And that cell, because I just pulled the rows of the table out of the probability table output by the network, the values in each of those cells are basically the probabilities of those symbols at that time, right? And now, what this means is that I can compute the probability of any given alignment is going to be, any alignment of beefy to the input is going to be a path from the top left to the bottom right. There's no alignment that's not represented in this graph, and there's no path in this graph that's not an alignment. So every path from top left to bottom right is an alignment of my symbol sequence to the input. And corresponding to every path, there's a probability, which is simply the product of all of the probabilities in the path, right? And so what you're really asking is, here's this graph, and in this graph, every node has a probability assigned to it. There are paths from the top left to the bottom right, and the probability assigned to that path is going to be the product of all of the probabilities of the nodes on the path. And so if I want to pick the most likely alignment, you just want to find the path which has the highest probability overall. And so now you've taken an alignment problem and converted it to a graph search problem, right? And so here, we've composed a graph such that every path in the graph from source to sink represents a valid alignment of my symbol sequence, compressed symbol sequence to the input. The node scores are the probabilities as computed using the neural network. The edges are assigned a score of 1. You're just sort of composing paths, right? And the score of a path any path in the graph is the product of probabilities of all nodes along the path. For example, the score of the subpath highlighted in blue is going to be y0b, which is the probability assigned to the symbol b at time 0 by the network, times y1b, which is the probability assigned to b at time 1, times y2e, times y3e, times y4f. So it's just the product of the probabilities of all the nodes in the path, right? And so a typical end-to-end path is going to be something of that kind. And our problem is finding the path from source to sink that has the highest probability. And the number of such paths can be very large. Well, I've said exponential over here. It's not quite exponential because the way I've composed the graph, any node can only have 2 children, right? Still, it's going to be extremely large, and you're going to have to search through all of those. So now, here's the problem. I've restated the problem as of finding the most likely alignment as finding the highest scoring path through this graph, right? If I give you this problem, how would you solve it? Yes, Chetan.
Of a different
Okay.
question. We could only do this in training, but not in
For inference, you don't know what the symbol sequence is, right? We're only speaking of training. We're speaking of aligning a symbol sequence to an input, period, right? So if you were given this problem, how would you solve it? I'm literally asking you to find the most highest scoring path through a graph. Do you guys know of any algorithms for this?
You could like use any graph search.
You can use pretty much any dynamic programming algorithm to find the best path through this graph, right? If you're computer scientists or electrical engineers, you know how to do it. If you're not computer scientists and if you're not electrical engineers, then you sit in the class for the next 10 minutes and I'll tell you how to do it, right? So here's what we can look at, right? We want to find the most probable path from the source to the sink. You can use a DP algorithm. And the most common one, popular one, is the so-called Viterbi algorithm, which looks like this. So it's based on a very simple principle, right? Now, let me just assume that I'm just going to draw the graph like so, right? All are so this is my graph, and these are all arrows. I'm not showing the arrowheads, right? Okay, so consider this guy over here, this node, right? So let's say I already know the best path to this node. So I know the most likely path from the source node to this node, however it may be, right? And I also know the most likely path from the source node to this node. Here there was only one option. Here there were 2 options, but I have done my computation already. And so I know the most likely, the highest scoring path from my source node to each of these 2 nodes, right? Now, observe how, as you keep extending a path, the score of the path changes by just multiplying the current, if I took any path, right? So the key point is this. If I took any path, if I extended this path to here, then the probability of this path is simply going to be the probability of this path times this node probability, right? Every time you add a new node to a path, the score of the path gets modified by just factoring in the probability of the latest node in the path. So if I want to find the most likely path to this node, now the most likely path to this node must be an extension of the most likely path here or the most likely path here. It cannot be anything else. It cannot be an extension of the second most likely path to this guy, because then, since you're simply sort of patching in the new node, that would still score poorer, right? So this means that for this guy, if I want to find out what is the most likely path to this node, I just have to find out which of these 2 guys scored higher and extend it. That make sense? Right? It's a very simple concept. And so the algorithm literally does this. At each node, you're going to sort of scan all of its parents, find out which parent had the highest scoring best path. Pick that one and extend it and say, okay, now this is my best path to my current node. That make sense to everybody? So it's a very trivial algorithm. So the way you would go about it is here. I can start at the first column. What is the best path to this node? Just itself. What is the best path to this one? There is no path to this guy, so you can kill it. There's no path to this guy because you always have to start from here, right? Then I go to the next column. I find out what is the best path to this fellow over here. There's only one parent, so it must be this. And so the probability of the best path is going to be the product of these two guys, right? Then what is the best path to this node? It's got to be this best parent, right? And so the probability of the best path to this node is going to be simply the product of these two probabilities. What is the best path here? None, because it has no parent that is alive, right? You can think of those guys as having 0 probability. Then you can go back here and say, who is my best parent? This one has only one parent, so the best path here must be an extension of this. And then the probability is going to be the product of the best path probability to this node and the probability of this node. Then you go down here and you say, what is the best path to myself? So what you would do is to check the two parents, find which parent had the highest scoring best path probability. Let's say it's this one, right? And then you'd say, okay, this is my best parent. You only have to keep track of the best parent. And then the best path probability to this guy itself is simply going to be the product of the best path probability to this node and the probability of the current node. And then you can do the same thing for here. You can say, who is my best parent? Retain a pointer to the best parent and then extend its probability to the current node. So you can keep doing this going left to right, going down each column, left to right, and at each time, you very conveniently just find out who the best parent is. You don't have to go looking all the way back, right? Since you're guaranteed that your best path is going to go through your best parent. So at each time, all you really need to do is find out who the best parent is. Retain that information. And then compute the probability and then extend the best path probability of the best parent with the probability of the current node. So it's a simple algorithm. It's very trivial, and you're going to do it in order n times t, right? So basically here's what we do. The best parent. The best path to any node must be an extension of the best path to one of its parent nodes. This is a guarantee. Any other path would necessarily have a lower probability, right? And the best parent is simply the parent of the best scoring best path. So here's what you do. You dynamically track the best path and the score of the best path from source to sink for every node to every node in the graph. At each node, keep track of the best incoming parentage and the score of the best path from the source to the node through this parent, and eventually compute the best path from the source to sink. So if that didn't make a lot of sense, we can look at this through a nice example, visual example. So here again, just a notation. I'm going to use this representation y subscript r superscript s of r, right? So r over here is y subscript t superscript s of r. So the t over here is time, the subscript is time. The r is the row, which row it is, and the s of r represents which symbol it is. So here, for example, there are 4 rows, so r can take values 0 through 3, right? Over here, r can take values. This is r would be 0, 1, 2, 3, and observe that S1 and S3 are always going to be identical, right? Because E has been repeated twice. So YTS1 and YTS3 are going to be always the same in our example, okay? And now, at my initial time, you're only keeping track of the best parent, right? the best parent for that best node is basically there is no parent, right? Just itself. And the best path probability to that node is simply the node of the probability of the node itself. For the rest of the nodes, they're not possible. You cannot start from those places. So you can just say for completeness sake that the best path probability to those nodes is 0, right? Then you go down here to the next column, and then for each, at this time, you would go down from top to bottom, and for each of the nodes, you would identify the best parent. Basically, scan through all of the parents and find out which parent has the highest best path probability. Again, the thing you're keeping track of here is you're keeping a best path probability to the node. So the best parent to that node is null. It has no parent. The best path probability to the node is the probability of the node itself at this point, right? And then when you go down to the next time, you're sort of going through all of the nodes. And for each node, first you find out who the best parent is, right? And you store that information. Then again, because the previous column, in the previous column, you already computed the best path probabilities to all the nodes. You just multiply the best path probability of the best parent node with the probability of the current node. And then you get a best path probability for the node itself, right? And so the outcome is that at the end of this, you're going to have information about the best parent for each node, right? So you'd have this for the first node on top and the second node as well. As you sort of scan down, for every parent, every node, you're going to know who the best parent is, and you're going to also be able to compute the best path probability to the node, right? And so once you've done this for the second column, you know the best parents of each of the nodes, and you also know the best path probabilities for all of the nodes. Then you can go down to the next column, right? And for the next column again, you can, for each node, you can find the best parent, store that information, and then extend the best path probability of the best parent to the current node, right? By just multiplying the probability of the node itself. And you can keep doing this going left to right, all the way to the end. And then when you get all the way to the end, at each node, you have the identity of the best parent, right? And so you know that the final node must be this guy, because you're looking for paths from the top left to the bottom right, so you can ignore the rest of these guys. And so to find the best alignment, you can just track the best parents for each of the nodes going backwards. And so you'd find that this was the sequence of best parents going back. You started the final node, find its best parent, find that one's best parent, and you can work your way back, and eventually you're going to arrive at the source node, right? And so this sequence of this path now gives you the most likely path through the graph and corresponds to the most probable alignment of the input to your symbol sequence. It's very trivial. The algorithm itself is very trivial, right? And that's going to tell you that your most probable alignment is this one here. In my example, it's B in the first two-time instance, E in the second one, third one, for in the next two-time instance, and E all the way down, right? Thereafter. So we have found out how to align an input, a symbol sequence to the input. And okay, you have a poll. Okay. So Pokemon Hypno. Ketan, is the first statement true?
Yeah.
Okay. And Pokemon Hundur, that's Jackie. Is the second statement true? Pokemon Hundur. Jackie Bo. No. Okay. Pokemon Curlia is the
Oh.
third statement.
Honduo.
Okay.
Yes, it was true.
All right. And Pokemon Curlia, there's Hadiza is the third statement true?
No, it's false.
False. Thank you. Right. So do all of you guys agree?
Yes.
And so the Viterbi decoding finds the most probable alignment of a compressed sequence to an input. It's run on a table of probabilities constructed for the compressed sequence with one row for each symbol in the sequence derived from the probability table generated from the output of the recurrent network. And it doesn't select the most probable symbol at each time. That would not give you the most probable path, right? Because just picking the most probable symbol at each sequence has no guarantee that those things are going to connect up. Finds the most likely path. So I have some code for it. Anyway, I'll skip the pseudocode. So here's what happens at the end of it all. Viterbi decoding actually gives you the most likely alignment for the input, right? And now that alignment becomes a guess for how the symbol sequence was aligned to the input. And so if this was your best path, then you can just use that as your targets that you're training the model to, right? And so now you can use this new target. You started off with some initial random guess by your model. You initialized your model. You could use the model to align your input, your symbol sequence to the input. So now you have an alignment of the symbol sequence to the input. You can use this alignment as your target, and you can update your model, right? So basically what you're doing is this here. You are you started off with sort of an initial estimate of the model parameters and found the most likely alignments for your training data. Then you fixed your alignments, and then you updated your model, right? You can use those alignments and update your model. And so and when you update the model, you're going to compute the divergence at each time, the divergence of the alignment to this symbol sequence, which is going to be the sum of the divergences at each time. So here's the key bit. Once I align my symbol sequence to the input, it becomes time synchronous, right? And because it becomes time synchronous, I can simply write the divergence between the two sequences as the sum of the divergences at each time, your standard KL divergence across entropy. And if I'm using one-hot representations for the to represent the target, the symbols, right? Then the KL divergence we know simply becomes the negative of the log of the probability of the target symbol, right? So basically what this would become, what the divergence would become over here is minus log y0b minus log y1b and so on, right? You're just going to be taking the negative of the log of the probabilities of all the symbols in the best path. And so if I compute the derivative of this divergence with respect to the output of the network at any time, the network itself is computing probabilities for every symbol, right? So this derivative vector is going to have as many entries as the number of symbols in your vocabulary, which can be much greater than the number of symbols in your sequence. But the derivative of this divergence with respect to any particular symbol is going to be either 0, or if the symbol is there in your target sequence, then at any time, it's simply going to be minus 1 over the probability assigned to the target symbol at that time, right? So this is just your standard KL divergence. So if you look at the at time, say here, 4, right? Your target is now F. So the derivative of the global divergence with respect to the network outputs, as we know from previous classes, is simply going to be minus 1 over YFF, right? Just the one symbol. So you only get a non-zero derivative for the target, for the class label. For all the rest, the derivatives we know are 0, right? So this is simply going to be a vector of zeros with one entry, which is non-zero, which is the entry corresponding to the symbol that aligns with the input at that time. And so the derivative of the overall divergence with respect to the network output at any given time is just this vector which is all zeros except for one entry, which is the symbol assigned to the input at that time. And you can use that for backpropagation. So the overall training algorithm would be something like this. You'd initialize your model or your alignments, then use those to find, you typically initialize your model, find your alignments, use the alignments, train the model, use the model to go back and re-estimate the alignments, and repeat this until your alignments stop changing or your model parameters stop changing, right? Now, again, this equation is going to be key. I know that I haven't actually been very clear about it, but the fact that the derivative of the divergence of a given alignment with respect to the output of the network at any time is simply a vector which is all zeros except for one entry, and that one entry is minus 1 over the probability of the symbol assigned to that time, right? This is something that we're going to use quite a lot in the next class. And so this would work, right? Now again, if you're thinking of things in terms of SGD, right? Now you could do one of two things. You could update your model and then try to align all of your training data and then use the new alignments to update the model and repeat the process, or simply update the model and use the updated model for the next training instance, right? So do this batch propagation. It all works. Yeah.
So we're doing this algorithm because we don't have the time sequence.
Exactly. Right.
We just have the symbols.
We just have the symbols. And this works. This actually, if you have a lot of training data, this technique is very simple and actually works very well, except for one problem. And the problem is that it depends, since you're guessing alignments each time, it's going to be very heavily dependent on your initial guess for alignments. And that is going to be dependent on the initial estimate of your models. And that means that you run the risk of very quickly running into local optimum, something that you really do not want to do. So an alternate solution is to not actually try to guess the alignment. And this is what we'll be talking about in the next class. Our instructor for the next class is here. So thank you all. And I'll see you on Wednesday.